All right, today we are diving into something truly beautiful and, honestly, incredibly powerful in the world of theoretical physics, conformal field theory. We're going to break down the core ideas piece by piece so you can really see what makes this whole framework tick.
But first, let's just start with a simple question, but one that's actually kind of profound. What if a physical theory had no fundamental length scale? I mean, what if the laws of physics were exactly the same whether you were looking at something the size of an atom or something as vast as a galaxy? Well, welcome to the weird, scale-invariant world of conformal fields theory.
Okay, so here's our game plan for this journey. First, we'll get a handle on CFT's unique coordinate system. It's like learning a new language. Then, we'll talk about symmetry and this really cool consequence called conserved currents. After that, we're going to jump into the deep end, the quantum world, and see what happens when operators get too close. We'll uncover the quantum rules of the game, and finally, we'll meet the real stars of the show, the primary players. So, first things first, let's talk about the coordinate system. To really wrap our heads around CFT, we've got to learn to speak its language. And trust me, it's a very elegant one. So right off the bat, here's the first big trick CFT pulls. Instead of messing around with separate coordinates for space and time, we just combine them. We use a single complex number z and its partner, z bar. This one simple move cleans up the math in a way that's hard to overstate. It's just cleaner. And here is the immediate payoff. You see, there's this really important thing in physics called the stress-energy tensor. You can basically think of it as the master blueprint for how energy and momentum are moving around. And in our new complex language, this messy, complicated object just splits. It breaks perfectly into two independent pieces. One part, T of z, only cares about z. That's the holomorphic part. The other only cares about z bar, the anti-holomorphic part. It's like taking a hopelessly tangled rope and finding it just falls neatly into two separate strands. It makes everything so much easier to work with.
All right, let's build on that. Now we get to see how this all connects to symmetry and conserved currents. This is really the classical foundation that everything else rests on. You know, at the very heart of physics is this beautiful idea from Emmy Noether. It basically says that any time a system has a continuous symmetry, like it doesn't matter which way you rotate it, there has to be a corresponding quantity that's conserved. That thing is called a Noether current. It's really like nature's most fundamental law of bookkeeping. If the rules don't change when you do something, then something else has to stay the same.
And here it is, the big connection. Remember that holomorphic piece of the stress tensor we just talked about, T of z? Well, it turns out that is the Noether current. It's the very thing that stands guard and enforces the symmetries of the theory, especially that all-important scale invariance. T of z is the official guardian of the rules.
Okay, so we've got the classical groundwork laid out. Now it's time to take a deep breath and make the quantum leap. Let's see what happens when these things we've been calling fields become quantum operators, and they start to collide. And you know, the source text itself says it best. So far, our discussion has been entirely classical. We now turn to the quantum theory. This is the moment we shift gears, moving from smooth, continuous fields to the chunky, probabilistic world of quantum operators. And this is where things get really, really interesting. So the most powerful tool in our quantum CFT toolbox is something called the operator product expansion, or just OP. You can think of it as a definitive rule book. It tells you exactly what happens when you smash two quantum operators right up against each other. And instead of getting some kind of complicated singular mess, the OP lets you just replace them with a nice, orderly sum of single operators. Now, I know this formula looks a little intimidating, but let's just translate it into plain English. On the left, you've got two operators, O1 and O2, getting uncomfortably close. The OPE is telling us we can just swap that whole interaction out for the sum you see on the right. That sum is made up of new single operators, OK, and each one has a coefficient, C, that tells you exactly how much it contributes to the final result. It's literally a recipe for what new thing is created when two other things collide. And here's a really great way to visualize what's happening. Imagine you have two operators inside that little circle. As you shrink the circle down, closer and closer to a single point, the OPE is telling you that those two operators basically merge together. They start to act just like a single, new operator sitting right there at the center. It's an unbelievably powerful way to tame the infinities that usually drive physicists crazy in quantum field theories. So, we've got this amazing tool, the OP. But that raises a question, right? How does that beautiful symmetry we talked about earlier actually survive in this messy quantum world? Well, that brings us to our next section, the rules of quantum symmetry, which are called word identities.
So let's see how our two big ideas, those symmetry currents and these operator collisions, finally come together. We started with a classical idea. A symmetry gives you a conserved current. Now we're going to see that idea get a major promotion. It becomes a fundamental law that governs pretty much everything in the quantum theory.
So, what exactly are these word identities? You can think of them as the quantum mechanical version of Noether's theorem. This equation is what forces all our quantum calculations to respect the classical symmetry. It does this by putting really strict constraints on something called correlation functions, which are basically just how we measure the relationship between events happening at different points. If your theory has a symmetry, the word identity makes sure your correlations show it.
And this is the truly incredible part. The word identity is so powerful, so constraining, that it actually tells you the most important part of the OPE between our guardian of symmetry, T of Z, and literally any other operator in the theory. It's amazing. If you know the symmetries, you automatically know the ground rules for how the stress tensor interacts with everything else.
This incredible power leads us right to our final and maybe most important topic. Now that we know all the rules of the game, we can finally identify the true stars of the show. Let's meet the primary players, the fundamental building blocks of conformal field theory.
So what does it take to be a primary operator? Well, these are a very special, almost privileged class of operators. What makes them so special is that when you perform a conformal transformation, like scaling or rotating, they transform in the absolute simplest, most elegant way possible. These are the atoms, the fundamental Legos that you use to build everything else in the theory.
And this right here is the mathematical fingerprint of a primary operator. When our symmetry guardian T gets close to a primary operator O, look how clean the OPE is. The terms on the right are simple. There aren't any messy or more complicated singularities. That simple, well-behaved nature is precisely what defines it as primary. It's the mathematical version of a model citizen.
And here's why that simple OPE is such a huge deal. Because that interaction is so clean, it leads to this equally beautiful and simple transformation law. This formula tells you exactly how a primary operator changes when you zoom in or rotate your perspective. And that predictability, that control, is the key to what makes CFTs solvable. We can actually do calculations and get precise answers, which, believe me, is a rare and wonderful thing in quantum field theory.
Wow, okay, we have covered a ton of ground. So let's just quickly recap the main story here. First, CFT uses the clever trick of complex coordinates to make the physics way simpler. Second, the stress tensor, T of Z, is the guardian that enforces all the theory's symmetries. Third, the OPE is our rule book for what happens when quantum operators collide. Fourth, word identities are the quantum laws that make sure those symmetries are always obeyed. And finally, it all comes down to the primary operators, the simple, elegant building blocks of the whole theory.
So, we've met the building blocks, and we know the rules they have to play by. And that leads me to the final question I want to leave you with. If these primary operators are the fundamental building blocks, what kind of amazing things can they build? Well, the answers range from the physics of boiling water hitting its critical point all the way to the quantum nature of black holes. The applications are as profound as the theory itself.